Hello, it's Tuesday again. It's Johannes here with Packet Tuesday. Today, by popular demand, we'll talk about some IPv6. If you do have any packets that you would like me to talk about, well, let me know. Leave comments in the videos or send me an email. I'll actually write down my email address in a second here, so you got that. But yeah, IPv6. I have to admit I have a little bit of a love-hate relationship with IPv6. Sometimes I really love it. Sometimes, well, it just doesn't work too well. And maybe the router advertisement packet we'll look at today will explain some of that. The router advertisements themselves, I often describe them as DHCP light. In a normal IPv4 network, like a little home network or such, you typically have a DHCP server that gives you the router, an IP address, and your name servers. Router advertisements will replace all of that. There is still DHCP v6, and we may talk about that in a future session here. Today we'll just talk about router advertisements. So an IPv6 router will periodically advertise itself, or it will respond to router solicitations, where a host on the network will ask, hey, is there a router here in the network? The closest to this we had in IPv4 was zero configuration. Zero configuration and in general the need for a DHCP in IPv4, there's sort of two reasons for that. Reason number one, in IPv4, we may have to reuse IP addresses. In IPv6, you never really need to reuse IP addresses because at the very least, for a local network, you have 64 bits of IP address space, so 4 billion squared addresses. In IPv4, you often deal like with /24s, and even in a home network, if let's say you have like 10 plus hosts in your network, but then you keep switching hosts, you have friends come over and such. So there's a chance that you'll run out of these 256 or 255 addresses that you have available in your local network if you have a /24. In IPv6 with 4 billion squared hosts, well, I don't think you have that many friends to come over to exhaust those addresses. The other reason that sort of made other approaches fail in IPv4, like zero configuration, is you may not have multiple IP addresses per interface in IPv4. So you're kind of stuck with that 169.254 address. You can not like get a second address, like a global address, something like this. So that's different IPv6. In IPv6, it's very normal to have multiple addresses per interface. But with that, let's switch over here to our packet and just pull that up here and switch. Okay, so here you got the router advertisement packet. Note how I just limited to first 5 lines here, so I have space for my IPv6 header diagram here. And if you look at the diagram, it's a lot simpler than what we had in IPv4. IPv6 more focuses on the actual routing part. So first of all, the IPv6 header has a fixed length of 40 bytes. There are no options in IPv6. We have something a little bit similar called extension headers, but they work different, and maybe future episode we'll talk about some extension headers here. But let's take a look at it. So, of course, it starts with version 6, and then a little bit odd, so we don't have that length field, that header length. Instead, we go straight to the traffic class, which is here 00. And the closest to the traffic class is the type of service in IPv4. And actually, it works very similar to the more modern definition of the type of service. Then the next 20 bits to sort of get us to line up again here at the proper byte boundary we have the flow label. It's also all 0 here. The flow label helps routers with more consistent routing. In IPv4, in order for a router to figure out if a packet is part of a traffic flow, it has to look at things like port numbers and such. So it has to look at your TCP and UDP headers, which routers, of course, don't like to do. There's a lot of extra work involved in this, even more so in IPv6. So the flow label allows us to identify traffic flows just based on the IPv6 header. Then we have our payload length. That's now 0080. So that's 128. Subtle difference here from IPv4. In IPv4, this was the datagram length. It included the IP header. In IPv6, this does not include the IP header. So it's anything beyond the IP header. And of course, you also see this then here in the TCP dump output. Next, we do have our next header, 3 alpha. Closest to this in IPv4 would be your protocol. In IPv6, instead of having your protocol like ICMP, UDP, TCP as next header, you may have an extension header. That's like these options. So that's why this got renamed. Here, 3 alpha is 58 in decimal, and that's ICMP v6. ICMP v6 on the surface looks very similar to ICMP v4, but there are some substantial differences and additional features in ICMP v6. That's why it's really a completely different protocol. ICMP or ICMP v4 is protocol 1, ICMP v6 is protocol 58. And then finally, we do have our hop limit. The hop limit is, well, your TTL. So just like in IPv4, it gets decremented by 1 in each router that handles the packet. Why is this 255 here? Well, this is a little security feature for these router advertisements. We want to avoid that an attacker from outside of our network is spoofing router advertisements and injecting them into our network. To prevent this, the hop limit must be 255. If we do see a router advertisement inside our network with a smaller hop limit than that, well, we'll ignore it. Because this is the maximum hop limit that we can possibly set. So any packet coming from outside our network has to have a hop limit of less than 255. So simple security mechanism here to basically make sure that the packet is originating from inside our network, and that we can discriminate against packets injected from the outside. Next, we have our source IP. That's here FE8 to 4 Charlie 29. Try a different pen here. So FE8 to Charlie 429. That's the address of our router. Addresses starting with FE8 are linked local only. That's another reason why this can't be injected sort of from the outside. And we need to have the linked local address of our router because, well, we need the router to be in our local network. Otherwise, well, we would need a router to get to the router, and that wouldn't really be all that helpful. So this is how we figure out what router to use. The destination address here, that's this FF02::1. FF, that's multicast in IPv6. FF02, that's link local multicast, so it's not being routed. And then FF02::1, that's all local hosts. That's the closest IPv6 has to broadcast. So this packet, the router will send it periodically. It will advertise to the local network, hey, I'm your router. And then a bunch of parameters we'll look at later. Okay, and then we have our ICMP header here. 8600, 86, let me just, I don't need this anymore. So 86 is 135, sorry, 134, 134. That's a router advertisement. The code must be 0. The RFC is fairly specific here. If this is not 0, you must discard the packet. And that's a little bit more, like IPv6 starts to be a little bit more specific than IPv4 to avoid some of these issues that we had with IPv4 where the code wasn't defined and some firewall rules wouldn't really block all the packets they were supposed to. We have our checksum, and then we have the actual sort of router advertisement starting here. So anyway, that's the IP header and sort of part of the ICM or the ICMP header. Now let's dive into the actual router advertisement payload. I want to use Wireshark for this, but before I pull up Wireshark, let me just show you something a little bit here with TCP/dump. If I add a couple verbose options here, you see how TCP/dump actually tears this packet apart pretty nicely. I'm still going to use Wireshark. It's a little bit prettier and also has a tiny little bit more detail, but there is not a big difference between what Wireshark and what TCP/dump here tell you about these router advertisements. So anyway, let's pull this up in Wireshark. So here I got it in Wireshark. The router advertisement, you see the source and destination. And here we have now our payload, so 134, that was the type. Code 0, the checksum, Charlie Echo Echo Alpha, the same we had before. The next we have this current hop limit, 64. Remember we had a hop limit in the IPv6 header here, 255, and I told you it has to be 255. So what's this hop limit about? 64. Well, this hop limit tells you what hop limit to start out with. So hosts on the local network, when they see this router advertisement, they will now send packets with a hop limit of 64. In IPv4 for the TTL, it was kind of up to the operating system. Windows like to use 128, Unix like to use 64 as its starting hop limit. In IPv6, it's up to the router kind of to tell you. And everybody here sets it to 64. If this is set to 0, then it would still be up to the host to pick the hop limit. Next, we have a bunch of flags. The managed address configuration flag. In addition to router advertisements, you may have a DHCP server. This flag tells you, hey, there may be a DHCP server to get an address from. The implementation is a little bit odd of this flag. Linux, for example, even if you have this flag, it does not automatically spin up a DHCP client. You still have to manually configure a DHCP client. In my experience, Windows and OS X always run a DHCP v6 client. So it's to some extent kind of ignored, that flag. Next, the other configuration. So managed address tells us there's a DHCP server that may give you an address. The other configuration tells you that the DHCP server may not give you an address, but it may give you other parameters like DNS servers and such. If the managed flag is set, the other flag is ignored because once you talk to the DHCP server, well, it may give you back addresses and other stuff. The home agent, IPv6 has an interesting option, mobile IP, where I can take my IP address with me. This basically will tell me that this router is usable to then notify the router and tell it about my current IP address so it can forward packets to me. The preference is actually a little bit an interesting definition here. It's 2 bits, but it's actually a signed 2-bit integer. And let me pull up the RFC here. Yeah, here is the RFC. So 1 means high, 0 means medium, and that's the default. And then we have 1 low. So basically, I think they wanted to stay compatible with the default 0 for medium, because these flags weren't defined initially. And if they're not defined, they're usually set to 0. So the default should be medium. And then we have basically 1 for high. And so this is a sign it's really -1 then for low. Yeah, and there's 1 0 that just reserved that. And it also says then here that 3 stage should really be enough. But anyway, so if you have multiple routers, this could basically sort of establish a little hierarchy between those routers. And here it's set to high 1. The proxy flag, this is set if you have like a bridge or such that between network segments that forwards, that proxies these router advertisements. And the reserved one here is not used. Then we have a router lifetime. So I told you that the router will periodically advertise itself. It will send these packets, and I think I have it here configured to like every 4 seconds, something like this. But this basically says, hey, this particular information is valid for 12 seconds. If you don't receive another advertisement, then forget about this router. The reason I have it set pretty short is just to make it easier to capture packets. Often you have this set for a longer time. Really depends. Some large networks set it to a very short time, because that way the router just keeps broadcasting those advertisements, and the hosts don't have to worry about solicitations and sending out, basically waiting for it. Reachable time and retransmit time. This is, again, something that allows you to manage a network a little bit. One problem we had in IPv4 was sort of ARP traffic taking over when you had a very large network. IPv6, for that reason, got rid of ARP. We have now neighbor discovery that sort of fulfills the same role. But to further be able to manage this process, the reachable time basically tells us if we realize a host is reachable. So we got its MAC address, that neighbor discovery succeeded. This is for how long we should assume that the host is reachable. And then a retransmit, if we send a neighbor discovery packet and don't get a response back, how long should we wait till we try again? So, and notice that these 2 times here are in milliseconds, while the router lifetime here is in seconds. And these times being 0 just means I don't set anything here. I leave it up to the operating system to come up with this. But you can see how for sort of very large static networks, you may want to set a larger time here to cut down some on the chatter of these network discovery packets. Okay, so this is basically your header for these router advertisement packets. You always have these fields, and next we have options. The first option we have here is prefix information. Just expand this all here. So this is a prefix that we are using here on our local network. So the router does not just advertise its address, it's also advertising the local prefix. So type here for the option is 3. The length is 4 times 8, so 32 bytes. In IPv6, everything is typically in 8-byte units, just like in IPv4, everything was in 4-byte units. First, we have the prefix length, 64 bits. And that's very normal here for prefix length in IPv6. And then we have flags on link. This means this prefix is link local. So I can talk to hosts in this prefix directly. I don't have to go to a router. The autonomous address configuration. If this is set, it tells me I should pick an address within this prefix for myself. This is not set here. It's set to 0, which means I can reach those hosts, but don't use one of those addresses. This can be used to make sure that you only get an address from DHCP v6. I found this to be hit and miss. Some operating systems will basically ignore that and still pick an address in this prefix. Then the router address flag. I mentioned earlier this idea of mobile IP. So when I told you, if I now move to a different network, I have to notify my home router that, hey, please forward all traffic for my IP address to this new network. In order to do this, I need to know the publicly routable IP address of my router. So far, I only have here the link local address. This is not publicly reachable. If this flag is set, it means that this prefix here is actually the address of the router. And then I just ignore the last bits, the last 64 bits, and I know the first 64 bits, because my prefix here is 64, are the local prefix. The remaining bits are just telling me what the IP address is of the router. This is cleared here. I'm not doing mobile IP here. And you see then just the remaining 64 bits are just all 0. Okay, then we have some reserved bits here. And then these lifetimes. So if I pick an address from this prefix, how long is this address good for? How long should I use this address? This is not a lease. This is not a DHCP lease. And it is purely advisory. I could use different timings here. But what modern hosts typically do is, if they pick an address from a router advertisement, the old way of doing it was I just used the MAC address for the last 64 bits. People didn't like that because of privacy and such. So what currently is being done is you just pick a random last 64 bits. And when you start using the address, it's the preferred address. The preferred address is the address being used for new connections. Okay. After the preferred lifetime is over, which I believe is a day here, after a day, I stop using this address for new connections. It now becomes a deprecated address. I may still use it for existing connections, and if there is some software that I started up that started using that address and it needs to set up new connections and can't switch to a new address, then you may still use that address. You may use it until that valid lifetime is over, which is 1 week. So what you typically see if an IPv6 host has been up and running for a while is that you'll sort of see, 7+ addresses here. You see a bunch of deprecated addresses that are no longer used for new connections. You see a preferred address that is the last one sort of it used, and that's not going to get used for any new connections. Okay, and then we have our prefix here, and that's here the prefix that is assigned to this particular subnet. Notice here the last 64 bits are just 0. So that's where I would fill in my local address. Okay, so that's the prefix. And the next that may give you then the address, in particular if that autonomous bit is set. If the autonomous bit is not set, then it just informs you that these IPs are locally reachable. And you don't have to go through the router for it. Next here, so in addition to an address, in DHCP v4, we typically get a DNS server. And we also get this here from the router advertisement. So we have a recursive DNS server option, option 25. It's 40 bytes here because we have 2 addresses. There's again a lifetime here. How long are we going to remember that? And that's just the retransmit time. That's how often I should see these advertisements coming in. And then you have the IP addresses for the two DNS servers in the network. Very similar. You can also have the DNS search list option. That's a more recent option, but just like DHCP or even in your resolve.conf, you sometimes specify a list of domains that you if you just have a host name, that you automatically append. So I have one domain here in that list. And then we have the MTU. That's the MTU we should use on the local network. So that's also configured here via router advertisements. 1500, of course, here the standard default Ethernet MTU. And finally, we do have our ICMP, our MAC address for our router. So that way we don't have to look up the MAC, we don't have to do a neighbor discovery for our router's IP address. We already have that. And that's here our option 1. So just to summarize here quickly. With router advertisements, we do get what's the local network. We know what's reachable locally. We do get a bunch of parameters like hop limit, how long should we remember MAC address and such. With these router advertisements, allow you to manage the network and reduce some of the overhead for things like neighbor discovery in your network. Neighbor discovery router advertisements actually part the same standard, so may make sense if next session we look at neighbor discovery packets. If you have any questions, anything that I should cover more with IPv6, let me know. Let me know, and I'll gladly do so. So anyway, that's it for today. I promised to give you my IP address. Let me just, not my IP, my email address. Let me just do that quickly here. So if you need to reach me, I'll also try to add this to the show notes. So that would be my email address. Thanks for listening again. Please subscribe, tell your friends, tell your enemies, and talk to you again next week. Thank you.